Welcome back. In this lecture, we'll be talking about the graphs of logarithmic functions. We've already looked at graphing exponential functions using transformations. We'll be doing the same thing for logarithmic functions. We'll graph them with transformations. But the first thing to think about here is what would the graph of an exponential function look like, and how does that relate to the graph of a logarithmic function? So we know what the graph of an exponential function looks like. That part we know. It would look either like this if the base were larger than 1, or it would look like this if the base were between 0 and 1. We also had all these properties that we had for our exponential functions. We knew that the domain was all real numbers, the range was positive numbers, we knew that we had a horizontal asymptote, y equals 0, we knew that we had a y-intercept. We also know that there was no x-intercept. We had those 3 good points. So we knew lots of things about the graph of anything to the power of x. Now, if we're thinking about the equivalent logarithm, the idea here is since it's the inverse of an exponential function, then everything x and y related will switch, which means that whatever the domain is for a to the x, that would be the range of log base a. Whatever is the range of a to the x, that would be the domain of log base a of x. Since you have a horizontal asymptote for an exponential function, y equals 0, then switching that to x equals 0, that becomes a vertical asymptote. Since you've got an y-intercept with no x-intercept, then you've got the reverse, an x-intercept with no y-intercept. Also, since the y-intercept is the point 0, 1, that tells you that you have the point 1, 0. Remember, we're switching x's and y's, all x and y properties, all x and y coordinates. And that means that if you know the 3 nice points for an exponential function, switching those x and y coordinates gives you the 3 points for your logarithm. So the exponential function, for example, has the point 1a, so the logarithm has the point a1. And same thing with the other points, that again, we're just switching out the x and the y coordinates. All right, so for the first problem here, this is us finding our domain of this logarithmic function. We have log base 2 of this expression, x squared minus 5x plus 6, and we want to know what the domain is. And so one thing that we know is that the domain would have to include only the values of x, which makes the inside not negative. So for the domain, you know that this x squared minus 5x plus 6, that it needs to be strictly greater than 0. Because of course the domain for a logarithmic expression log base a of x is the inside x needs to be greater than 0. So for a logarithmic function where it's not just the inside is x, where it's some function of x, that function of x needs to be larger than 0. So now we're kind of at the end of chapter 5, where we did the solving rational or polynomial inequalities. This would be a moment where I might just sort of on the side mention to myself that if I'm thinking about the equation y equals x squared minus 5x plus 6, that would be the equation of a parabola that's opening upward and has x-intercepts of 2 and 3. So if we're interested in where is this x squared minus 5x plus 6, where is that greater than 0, that's the same as asking where is this parabola above the x-axis. And the answer is everywhere except for between 2 and 3. Between 2 and 3, it must be below the x-axis because it's a parabola opening upward. But to the left of 2 or to the right of 3, for those parts, that parabola would be above the x-axis, which means that either x is less than 2 or x is greater than 3, that any of those values of x would be a value of x that has that parabola being above the x-axis, which means it would be something where it would have a positive value. All right, so now what we're going to do is graph here two functions. We're going to graph y equals 2 to the x, and we'll also graph this log base 2 of x, and we're going to do this on the same axes. So I'll start with my exponential function 2 to the power of x, and then I'll work on my logarithm after that. For 2 to the power of x, we know the points that it has that it goes through. It should go through 0, 1, 1 comma the base, which is 2, and negative 1 comma 1 over the base, which is negative 1 comma 1 half. And that we would have a horizontal asymptote of y equals 0. So there we go. This is my graph of y is equal to 2 to the x. And actually, I'm going to just revise this a little bit here. I'm going to just take that label that I have of the 2 to the power of x and this point. I'm just going to move them over because when I graph my next part of the graph, I think I'm going to run out of room if I don't do that. There we go. So here I've graphed y is equal to 2 to the x, and when I graph my next function, log base 2 of x, I'm going to switch to a different color here. Let's go, I'm going to graph this in sort of that browny reddy color. When I graph this, I'm going to be taking all three of my points and switching the x and the y coordinates. So we have the point 1, 2 on our exponential graph, so the point 2, 1 should be on our logarithm. You have 2, 1. You have the point 0, 1 on your exponential graph. Your point 1, 0 should be on your logarithm. You have the point negative 1 comma 1 half on your exponential graph, so the point 1 half negative 1 should be on your logarithm. We had a horizontal asymptote y is equal to 0. So for the logarithm, we should have the vertical asymptote x is equal to 0. Just to be careful here, if you're wondering about this, this is two separate graphs graphed on the same axes. So in case you're worried about, wait, it looks like my vertical asymptote is going to cross through this graph. Yeah, it certainly is, because that vertical asymptote only applies for this logarithm. The logarithm has a vertical asymptote. The exponential graph does not. So although it looks like this vertical asymptote is about to cut through that logarithm, that exponential graph, that's fine, because again, that vertical asymptote doesn't apply to that exponential graph. Just in the same way that this horizontal asymptote doesn't apply to this logarithm. In case you're wondering why are we not tapering off to 0, that's because that was only for the exponential function. So we have here our graph of y is equal to log base 2 of x on the same axis as our graph of y is equal to 2 to the power of x. And same as we said before when I was talking about graphs of functions and their inverses, that they should be mirror images of each other in the line y equals x. And that's exactly what we've got here. If you're looking at the exponential function, it is the mirror image of that logarithm reflected in that line y equals x. So now that we know what the basic shape is for our logarithmic graph, then we can use this to graph any function we'd like with transformations. If we're looking at this, we can see that there are two transformations that are happening. So the basic shape for this graph is going to be a logarithm base 3. And that we're going to be taking this graph and shifting it to the left by 2. And then we are going to vertically stretch it by a factor of 4. Okay, so first thing that I'll do is I'm going to draw my basic shape of log base 3 of x. So log base 3 of x will go through a couple of nice points. The first one being base comma 1. In this case, the base is 3, so the point 3, 1. It will go through the point 1, 0, and we'll go through the point 1 over the base, comma, negative 1, which is a third, comma, negative 1. We're going to have that vertical asymptote x equals 0. And our graph will look a little something like this. So this is our graph of y is equal to log base 3 of x. And now the first thing that we'll do here is we'll transform it by shifting everybody to the left by 2. We're shifting everybody to the left by 2, and that means that not only is the graph going to be shifted to the left by 2, but that vertical asymptote will also shift to the left by 2. So I'll actually take care of the vertical asymptote first. Since I know it's shifting to the left by 2, then I know that my vertical asymptote should be at x equals negative 2. And then for all the x coordinates for the points, we're going to subtract 2 from all of them. So the point 3, 1 is now at the point 1, 1. The point 1, 0, if we've shifted it if we've shifted it 2 to the left, is now at the point negative 1, 0. And then finally, if we're taking the point 1/3, 1, and we're shifting it to the left by 2, so 1/3 minus 2, that is negative 5/6, or sorry, negative 5/3 rather. So we have negative 5/3, comma, negative 1. And I'm going to put my labeling over here, I guess. I don't have enough room. There we go. And now I will draw my logarithmic graph. There we go. And now I just need to label it. I'll label it over here. Y is equal to log base 3 of x plus 2. There we go. So we've done our transformation of shifting to the left by 2. And now the last thing that we'll be doing here is doing our vertical stretch. A vertical stretch by a factor of 4. So we're going to be taking all of our y coordinates that we have, and we're going to be multiplying them by 4. So if we're thinking about the graph itself, a vertical stretch of a vertical line isn't going to change the vertical line. So our vertical asymptote rather will still be x equals negative 2. Also, the point that's on the x-axis, the y-coordinate is 0, so when we stretch it, it'll still stay on the x-axis. But this first point, 1, 1, will move up to 1, 4, and the other point, negative 5/3, negative 1, will move down to negative 5/3, negative 4. So let's graph that. So we have still our vertical asymptote, x equals negative 2. Now we'll just take our points. We had the point 1, 1. We've stretched it vertically by a factor of 4 to give us the point 1, 4. We had the point negative 1, 0. Multiply the y-coordinate by 4, it's still negative 1, 0. We had the point negative 5/3, negative 1, and we're multiplying that y-coordinate by 4 to give us the point negative 5/3, negative 4. And there we go. We've got our nicely stretched graph. This is y is equal to 4 times log base 3 of x plus 2. So one thing just to mention here, and I think it's good to just clarify this, because usually somebody will ask, what about the left side of the graph? Why is there nothing there? And again, this is something where we need to remind ourselves that unlike the exponential functions, they have a domain of all real numbers. For them, the range was only things that are positive. For a logarithm, the domain is only things that are positive, and that the range is all real numbers. So why is there nothing on the left side of the graph? That's because for this function, log base 3 of x, the domain is x needs to be positive. So there is actually nothing on this side of the graph at all. I haven't omitted part of the graph. There just literally is nothing there. There is no graph of f of x for those smaller values. Okay, so finally, we want to find f inverse of x. And if we're thinking about this, we know what we would normally do. We would normally start off with writing out y is equal to our function. So I'll do that. And then the next thing we normally would do is to switch the x's and y's. So that would mean that we would have x equals 4 log base 3 of y plus 2. And then the next thing we would do is try to solve for y. And once we've solved for y, we would have ourselves our inverse function. So let's do this. If I wanted to solve for y, the first thing I would do would be to divide both sides of the equation by 4, just to isolate that logarithm. And now I've got log base 3 of something on the right-hand side. I could rewrite this as an exponential equation with base 3, just swapping out my input and my output. For the log function, the input was y plus 2, so for the exponential function, the output is y plus 2. For the log, the output was x over 4, so for the exponential function, the input would be x over 4. And then now we just need to solve for y. So for our inverse function, that would be 3 to the x over 4, or 3 to the 1/4 x minus 2. So the fact that this is an exponential function with base 3 shouldn't be a surprise, because we know that the original function was a function built off of log base 3, and we know that the inverse of log base 3 of x should be 3 to the power of x. So the fact that I've got an exponential function with base 3 as my inverse should come as absolutely no surprise.